So welcome everyone to the 16th talk of the Higher Categories seminar. So this is also maybe the last talk of the year. So yeah, this is the part two of the first talk that we had on two categorical equivalence theorem A. So this is the second part, and the first part was basically some two categorical preliminaries, and I also talked about inferior localization a bit, but yeah. By the way, can you please pause the recording for a moment? Sorry. Right. So yeah. So after I know everything is resolved, so maybe I can start. So right. So this is the second part, as I said, second part of the talk. So here's the plan. So yeah, I'll start with a few recollections of the like the few main ideas of the part one part, and then I'll talk about the relative two-nerve construction. Then, like just for fun, I'll also talk about the street nerve and the way it's related to the relative two-nerve construction. That is, right? How can you see the relative two-nerve? How can you relate it? So, how can you see it as a two-categorical street nerve? In a way, well, I'll talk about that. Right. Then I'll talk about scaled simplicial sets and the scaled nerve construction and so on. And then right, so an alternate model that we'll need. So yeah, so turns out this isn't the exact model that we need. So turns out we need a different model. So I'll also define that. And then I'm not going to construct specific things. So maybe I'll get rid of this. I think it's okay to be. So I'll just talk about anyways, yeah, I'll talk about the vibrations and sections involved. Like I'll just give a description, so that kind of forms the backbone of the proof of the theorem. Then I'll state the theorem, and then there's one fun application that I'll talk about, right? So, okay, let's begin by recalling a few things. So, recalling a few things from the previous talk. So I had defined lax slice carpy. So is my writing big enough? Is it good enough? Hope it's okay. I think it's okay. So it is denoted by right. So you have a two category. So this is my category of two categories. So right, and X is an object of the two category. So for the lax slice category, the objects are just maps in C, right, and the one morphisms. So one morphism from right. So X is the one that we have. So let's consider two objects. So these are the two objects, right? So one morphism. So it is like so it consists of a morphism. Okay. Consists of a morphism. So maybe okay. Let me call this something H from Y to X with the two morphism. Yeah, please feel free to interrupt if there's something that I get wrong or if there's a question. Right. So with the two morphism and the two morphisms. So this is just a recollection. So yeah. So I talked about everything in details in the first time. So the two morphisms. So from say K. Okay, I've called this H. So okay, let me be consistent with notation. So H and beta to say L and alpha consists of a two morphism. So let me call this something, say eta, okay, eta. H to L such that the induced diagram, so this induced diagram commutes. So this is my beta goes to H O F. Okay, yeah. So I'll call this H. So okay, like that. So this map, okay, yeah, this map is H composite, and so we have defined alpha. It goes to composite, and so this commutes. And so when I say so that's a lax slice category. When I say an oplex slice category, so I'll just write it down. This is my definition of the oplex slice category. And now, okay, let me talk about. Okay, let me just briefly also talk about marked categories. So what do I mean when I say marked categories? Just briefly, marked categories. So yeah, marked. So it is just like a pair that you have, where C is a two category, and so this is a class of morphisms of the two category. It says that with all identities, it has all the identities. And so yeah, that's basically what I mean. Okay, so enough of recollection. So now let's get to business. So okay, so right, so let's talk about the relative to now. So relative to now, right? So we are interested in a two categorical generalization of Lorry's relative nerve functor that we have, right? So yeah, the reference is posterior and hatch, and also other things that other things that I'll maybe show later. Anyways, right? So yeah, I'll first start talking a bit about maybe there's a cool. No worries. Right. So yeah, I'll skip on the details on purpose. So I'll just outline the construction of the relative two now. So we already have. So this is like as I said before. So I'm just repeating what I said. So it is a generalization, two categorical generalization of Lorry's relative nerve functor. So yeah. So okay, let's begin with that first. So relative nerve. Okay. So X is a smaller category. So small category. And suppose we have a functor. So let me call this H next to simplicial sets. Right. So suppose, okay, takes into chi of A. So this is the this is the notation that I'll be using. This is like typical notation this use. So suppose we have a functor, right? Then the nerve of X relative to H. So this functor is a simplicial set. So okay, so yeah, this is the notation that is used. So now of X relative to X or relative to H. So this is the way I denote it. The simplicial set, which is defined as follows, right? So for all, so this is directly from higher to posterior. Yeah. So for all non-empty finite linearly ordered sets. So maybe I a map to H on X. Sorry. This is the data. So you have a functor. So let me call this lambda I to X. Then for any non-empty subset so maybe I prime. We have a maximal element so okay, maybe I dash on the map. There are reasons of calling it this. Oh, right. So page, okay, page and the functor, okay, it's lambda. Okay, and for non-empty subsets, J. Again, the maximal elements are denoted with the lowercase. Okay, let me write this down with J, lowercase j. So yeah, these are the maximal elements. J, sorry, very sloppy of me. J and I dash I. So these are the maximal elements that we have. So the following diagram commutes. The following diagram commutes. So this is your inclusion. Okay, so this will be tau of j, the way I have to find tau. Right, so here's the different tau. So tau of j. Right. So this has to commute. So maybe a remark. I mean, so this relative nerve construction. So it is like. So it is like you think about it as growth deconstruction of a contravariate functor. So maybe I'll just write that as a remark, and we'll see that that is something that is the way we define it relative to nerve, right? So maybe a remark. It's the growth deconstruction of the contravariant functor and so this is like the category that is spanned by infinity categories, right? So right, so yeah, from this, like so I think okay, let me I don't remember the exact section, but I think I'm pretty sure it's 3 point something. So right, so we can so we get equivalence actually. So okay, let me write it down first. So this is section 3.8, I believe 3.2 of isotopes theory. So I'm not getting into the details, right? So we get equivalence. Right? So So the thing is that upon passing on to infinity categorical localizations, right? So we get a way to identify the infinity category. So okay, let me write it down properly. So right, so we can identify the infinity category. So that's the norm of the opposite category CL, and and uh, and the category infinity cat. That is the infinity category of small infinity. The category that is spanned by infinity categories and Cartesian vibrations. So yeah, well, you can find the details in 3.2 if I'm not wrong. Right? So now, yeah, what is the point of? So okay, so this is the category of Mark simplicial sets. So I talked about Mark simplicial sets before, but okay, let me just define that real quick, maybe. So sorry, it is just a pair. So a Mark simplicial set is like a pair. A Mark simplicial set is a pair. So where C is a simplicial set, and so W is a set of edges from C, which contains every degenerate degenerate edge, which contains. So yeah, so it is like so yeah, it makes sense if you know what a marked category is, right? Every degenerate edge, right? So yeah, so what do I mean by marked edges? So the edges in W are the marked edges, right? So right. So yeah, so now let's talk about the relative to now. Relative to now. Right. So we want a generalization of the relative nerve to include. So as I said before, so this is the way we will look at or will have the relative two nerve construction. So by looking at it as a Grothendieck construction of the contravariant form. So right. So this is what we have when we. These are the kind of functors that we have when we are talking about relative nerves. So for relative two nerves, we also want to. So we want to generalize the relative nerve to include functors which look like this. Right. So we also want to have such functors where, C is a cat. Let me write this. C is a cat enriched category. Right. So yeah. So what is the idea? So I'll just first talk about the basic idea that you have. I mean, the way I think. The way you're supposed to think about it. So yeah, I won't claim it to be a way that just I think about. I mean, yeah, this is the way you think about it, if you understand. Okay. So right, so okay, so we have this functor. So to F associate, so those stepwise, associate a simplicial set. So again, so this is the notation that I'll be using. Fancy guy. Right, equipped with the map. So this is the map. Right. And now this, so what is the, okay, wait, let me write it down properly. So now this is, so now this is a scaled now, right? Scale 2 now. So yeah, I'll talk about scale now later. So this is, so you would have noticed that I also want to talk about the street now. So why do I want to talk about the street now? So it is like, so it is like a scaled version of the street now. So it is like a scaled version of the street now that I'll define next. So this is the way. So when you say a street now, okay, yeah, I'll define it in the next section. Right. So right. So the relative to nerve construction. So it is like an adaptation of, okay. So this So it is like an adaptation of the like typical relative nerve construction to two categorical world, right? Okay, so I'll just briefly define what I mean by a street nerve. So yeah, I mean, so the definitions of so there are a lot of unitality conditions. So yeah, I'll just give an idea. I won't define it. I mean, just because there is just because you can think about it as a scaled version of the street nerve. So that is just why I'm defining it. So it doesn't have any direct consequences that we know of. I mean, so it doesn't pop up in many places, right? So okay, the street nerve of a tri-category. So what do I mean by a tri-category? So it is like an algebraic version of the weak three categories that you have. A tri-category. So yeah, I won't get into the details. Tri-category. So okay, let me call this C. This is a simplicial set. And this is the notation that I'm using. Okay, so okay, I used the wrong font. Sorry. Right. So this is a simplicial set with n simplices being lax functors from the locally discrete tri-category associated to, right, so it's right, associating, I mean, maybe yes, associating this to C. So yeah, there are many unitarity conditions that I want to. So this is the basic idea. So you have these. So the n simplices are lax functors from this tri-category that you have, right? So yeah, so it just pops up. Yeah, we'll see more about this later. So this is just so yeah, maybe so yeah, it was not a definition, just an idea of what it is. I want to even spend time giving examples because of the time that I have. So okay, so now let's talk about what I mean by scaled simplicial sets. Right. Right. So I've defined a Mark simplicial set. Okay. So now I'll talk about scaled simplicial sets. Right. So right. So the thing for me is that so the deal is that the scale simplicial sets, so they provide a model for homotopy coherent theory of infinity two categories. Right. We call that the theory of infinity bicategories. So yeah, this is exactly the way we use simplicial sets as a model for a homotopy coherent theory for infinity one categories. So that is kind of where the interest comes from. Right? So infinity bicategory. So this is the model of infinity two categories that we get using scale simplicial sets. So okay, so I'll just go ahead and define one. So a scale simplicial set consists of simplicial set. K is a simplicial set with subset. So okay, I'll call this TH. We'll know why of K2. Sorry, of two simplices with degenerate two simplices. So yeah, okay. Why do I use TH? These two simplices are called thin, right? So thin, TH for thin, right? So these are thin two simplices, right? So okay, maybe some notational conventions. So for a scale simplicial set, L, we denote the simplicial subset of L with two simplices. Oops, I'm sorry. It's like more like a jump scare. With simplices, all of whose two simplices are thin. All of whose, two simplices are thin. So the simplicials are by, so we denote this by by TH and TH, right? So that's the way I denote it. So now for scaled simplicial sets, so L and TH, that is, right? So that is my that is my thin two simplices, right? So this is the way you write it, right? Scale simplicial set. Okay, and you take a marked simplicial set where, okay, let me call this C and A for the markings, and a map. So these are all the things that you have, C to L. Well, P is said to be a scaled Cartesian fibration. So it is said to be a scaled Cartesian fibration. If so, start from the main page. So first, so this map that you have P is locally Cartesian, local Cartesian fibration. So yeah, what do I mean by local Cartesian fibration? So it is like, okay, maybe I'll write that in the brackets. That is inner fibration, just to remind you guys, inner fibration such that, so yeah, it's an inner fibration and for all edges. So yeah, for this, L, okay. So we're working with L. Right, for all edges, the pullback okay, so it goes from C to K. Okay, so the pullback C. And so this pullback is our Cartesian fibration. No way, I didn't mess anything up. And the second one is that so there is this set of locally P Cartesian edges of X, and the last condition, the restriction of P, so this is the map that we have, to thin to simplex. Sorry. Okay, wait, I'm sorry. I don't know why I made it K all the time. Is a Cartesian fibration. All right. Yeah, there are a lot of things that I won't be talking about, but there are versions of like scaled versions of straightening and unstraightening, right? So I won't talk about anything. So that's not the point. So, okay, so now we are in a position to define a relative to now. So, yeah, so let me start with some notation first. So again, we take a finite linearly ordered set. There's J. So J, so J is a finite linearly ordered set. So we define a two category such that the objects are like these elements of this J, and the morphisms. Okay. So yeah, X and X tertiary J. So it is the poset of finite sets, just subsets of J, such that the minimum is equals to X and maximum is X dash. Oh, whoops. Sorry. There's just some sloppy writing. Right. And yeah, I mean, so the ordering is by inclusion. That is understandable. Right. So these are the morphisms and the composition on top. So right. So for X dash X double dash J. Right. So it just takes ordered pair union, right? So now, okay. So now I'll define the scale now. So maybe it is just a remark, right? So the way we are constructing this category that we have, so this extends to a co-simplicial to category. Co-simplicial to category says that for our two category, we can construct the simplicial set. So this is the scale now. Oops, again. Right. And now, so now some useful notation, because we'll be using this category a lot. It's an important notation. So for again, for a linearly ordered set J, so we consider the under two category. So yeah, I mean, I think in the paper they use D, but yeah, I'm more comfortable writing U. So semi notation maybe if you're looking at the paper as well, but isn't that difficult, I guess. Right. Oh, sorry again. Right. So it is so the way I have defined. So this is right. So this is this right. So like slice category. So you can look at it like that, right? So and the homotopy category is so for obvious reasons we'll see. And there's the homotopy category of this. So okay, sorry. This category I'll just call it U of J without the tilde. So the homotopy category is just this, right? Right. So, right. So yeah, there's a way we can think about this homotopy category as it's a fun exercise actually. We can do a lot of things with it. So it is like opposite, right? So you can view it as opposite. So maybe I'll just add it. So yeah, J as opposite. So if you want, I can maybe draw one as well. Okay. So okay, yeah, opposite. So elements are subsets, right? So elements are subsets such that J is equals to best, right? And so this is the relation that you have. Right? Right. So if you look for max elements and right. So maybe an example would be okay. So this is the way it looks. I think, yeah. Right. So this is the way it looks. Right. And now, an important proposition. Okay, so proposition. Again, so I is a non-empty, finite, linearly ordered set, and suppose you take a subset, then so we'll see that we'll use this later. So okay, let me call this proposition maybe star. This I guess. Yeah, we need this. Right. Then right. So pull back along one morphism. And the CI copy determines a pullback. Right. So I and I dash, right? So we have this pullback. Oh yeah. So again, it takes this back to the view. Right. So now getting to the definition. So again, so you take a two category, see, and again you take a functor. So it is a marked simplicial set enriched functor. So right, enriched functor. So then marked never go to this. Marked simplicial set. So okay, so this is the notation that we're using called the relative now of f is defined as follows. So an n simplex consists of, so this is our version. So this is our definition of a relative 2 now, but we'll be using a different one. This is the standard construction that we have. So we'll see an alternate version in the next section. So and n simplex. So maybe lambda. But I have to make sure that I remain consistent with the notation. Oh, wait. Yeah, C. Okay. This is C. Does it look like the C? And for all subsets of this, a map of marked simple sets. Okay, wait, there's some notation that I should have introduced, but I'm not. What do I mean? There's hash. Right? So okay, let me briefly define what I mean. Okay, so some notation. We'll write it down on the margin. So okay, so L is a simplicial set. Then L hash with the marked simplicial set whose marked edges are degenerate edges. So they are given by the degenerate edges, right? So this is what I mean by hash. See here, I take the hash of this simplicial set, right? So yeah, we have a map of marked simplicial sets. Says that it is a condition. There's a diagram that should commute, as you might have guessed. It says that for all the following commutes. Okay, so please point out a mistake if there's any, because I don't have this written anywhere, so I hope I don't mess this up. I am I dash. So if I get the first one right, then it's yeah, it seems to be good. Yeah. So you apply the map and lambda times the theta that I defined for the I dash. So then you get this. Let me write it down. Okay. So far, so good. Yeah. Yes, I think it's okay. It's cool. Yeah. So what is this? This is just the theta. Iterative function. Great. This thing right here. Yeah, I missed the lambda. Anyways, yeah. So this commutes, right? So yeah, so what are the markings, right? So yeah, okay, let me define the marking. So an edge of the simplicial set consists of a map H, say H and C, with vertices and an edge f of H. Yeah, so this is the map H. Stash, yeah, in f of x, right? So yeah, So E is marked when E tilde is marked. Right, which is obvious. Right. Then, okay, let me add a page. I'm not sure how much time do I have left. That's all. Okay, then, okay, let me continue. So yeah, so this is oops. So this is an observation. So this is a functor from this. We're getting a functor with marked simplicial set enriched natural transformations. And right. So yeah, thus you get this. Okay, let me write it down. We remember it is enriched in marked simplicial sets, category of marked simplicial sets. I don't know how do I move this, but okay. Let me do something funny. Just because I don't want to write this out again. Yeah, this is the scale now, right? Yeah. So now, right, so now we can use the adjoint functor theorem to get the following adjunction. So I'll just write the adjunction. So using the adjoint functor theorem, we can just apply that, and we'll get this adjunction. So this is the main thing, right? So yeah, I won't talk about the mode structures and stuff, right? But yeah. Right. So this is the adjunction that we are getting from the relative to nerve construction, but this is not the one that we'll be using. So we need an alternate model. So an alternate but equivalent model. Right. So yeah, we want a version of this guy that we have. So okay, so let me first call this something. So I'll just add the tildes to differentiate this version from the actual one. So everything else remains same. So I'll define all of them. So yeah, I think all this remains the same. Right. And so yeah, so what is the main theorem? So let me write the main theorem first. So main theorem of this section. So you have a two category. And so for all marked simplicial sets enriched functors, so again, right. So the map, so this is the main theorem, as I said. So eta. So this is so this tilde is the version that we want, is a weak equivalent of scaled Cartesian fibration. So scale now. Right. So yeah, this is what we want. So okay, so now let me go ahead and define the things. So right. So again, so it is we take a two category and so again it is a So a marked simplicial set, category enriched functor. Let's see. Functor. So we define our marked simplicial set. So the one with the tilde. So as follows. So an n simplex has, so it's like, so yeah, it is just like, all right. So an n simplex is like, so we can compare this definition with the previous, with the actual definition that we had. So you'll see that it's like more or less, very similar. And there's one catch that we'll see. Again, for substance, we have a map of marked simplicial sets. We have, so this is where it changes. So this is the hatch that I define. It says that for all inclusions, so yeah, the following diagram commutes will get a similar, the diagram similar to the one that we had before, like this one. Yeah, this diagram. So yeah, it shouldn't take much, shouldn't take a lot of time to draw that. Because yeah, more or less similar, 6.3 or so now you're taking the Duskinov. So N2 is the Duskinov for people who missed the first part. So it's the Duskinov, that's the two categorical version now that I defined previously. Okay. So this is the tilde. So we had defined this functor, right? So this is the, if you remember this, the proposition that I started, right? So this is just the tilde, like the version with the tilde. This is the one that we want for this version of this theorem. And yeah, we have a tilde here as well. Yeah, sorry. Right. And okay, so this is again the functor that we define. So maybe I can, otherwise I say it's okay. I think the notation is fine. And here again, we apply our, just give me a moment, please. Yeah. So I just want to make sure. Yeah. Right. So this is also more or less the same. So yeah, writing this down is not fun. But realized pretty quick. But yeah, we're almost there. Right. That's it. So this commutes. So this is what I mean by this version of marked simplicial sets. Right. And now, so it's maybe a remark. So yeah, the marking, okay, so the marking is the same, the way we talk about the edges being marked, so that's the same, exactly the same as we had in the previous case, right? The way we had defined it, right? Okay, so maybe a remark. So the maps So these induce a natural transformation of factors. Right, so get a natural transformation, which is pretty, seems pretty obvious. And it's a junction, so we denote that junction by epsilon, maybe. Right. Cool. So, yeah. So this is a proposition. Okay, so maybe because I still remember, so okay, maybe I'll give a proof of this. So yeah, this is exactly like the argument that's done in the original paper. There's nothing novel or new that I'm about to do. But yeah, it's seems pretty neat to me. So this preserves trivial calculations. But yeah, so it won't be a full proof, of course, and there'll be gaps that you should be able to fill. Right, so again, C is the two category, suppose, right? And so suppose we have pointwise, okay, so yeah, we need pointwise trivial vibration of simplicial set category enriched functors F to F dash. Right, so as we know, so again, I'm not getting into the details. So it is an ISO. So the map that we defined before, right? So this eta is an ISO on zero simplicities and one simplicities, and marked edges as well. Marked edges. So right, so we get okay. There's another thing that I can maybe I should have defined it or not. So some other notation. So again, for a simplicial set K, so this is my notation for this denotes the marked simplicial set, with marked edges being all the edges. Marked edges given by all the edges. Right, so right. So we get lifting problems, right? So lifting problems look like this. Okay, let me name this a star. F dash. And another one, maybe. Oops. Yeah, so the notation that I had used. Wait. F dash. So let me call this double star. So I see I'm running out of time. I think I'm almost run out of time. So maybe I'll take a few, I think maybe 15 more minutes, then I'll be done. So yeah, so now we'll use the proposition star that we have here. Okay, so maybe this is a star dash because I've already called the proposition to be a star. So okay, let's revisit that for a second. So we'll use that actually. So here's the proposition. Right, so we get a pullback functor like this. Right. So okay, so using that, so we'll see that So we can produce lifts. We can produce a lift of the previous functor that we saw to get diagram. So this is the diagram that we will get. Which makes sense, right? Right. Right. So this U comes to the picture. Right. Yes. Yeah. Okay. I think that's right. That's right. Anyways, right. So using this, right, then for an inclusion, we get a coefficient of simplicial sets. So which looks like this. Yeah, this makes sense, right? We're using 0 because you can lift it all the time. So right. Right. Okay. So now let me think. Let me pause for a moment. Right. So now, okay. So let's define. So okay, suppose this is this is so this is the nerve, right? So then let's define this, right? Yeah, I am kind of maybe a bit blurry on the details, I guess, but yeah, I'll try to be as complete as I can. So okay, let's denote it. Okay. So I think okay. Let me write the part that I know that I remember properly. So we'll get So again, this is more of a sketch, right? So we'll get this. So if I define right, and this UI, so it is like the so this is the so we got these cofabrications, right? So it's collection. So this is the way I denote it. So the cofabrications that you're getting. Yeah, I think this is right. Right. So then, so we can show that this, so this is the part where I am kind of missing. So we can show that. So the lifting problem of the form star dash that we had, so it is exactly, so it is, so such problems are bijection with these lifting problems. I don't remember how can we show this, but yeah, we can, this is what we do. Right. And which has a solution because this right, so because this is a cofabrication. So that's the way you prove it. So okay, So now let me be a bit faster. So again, so a few more things. I think we're almost there. A few more things. So maybe I won't get time to talk about the application I have. But okay. So let's define the simplicial set category enriched functor. So I'm just writing the functor. Uh, mhm. Right. So it takes an element to, right, again, it's like, this makes sense, right? So yeah, I won't be able to spell everything out loud. And so yeah, so the marked variant would be, so with the marking, so here's how the marked variant will look like. Again, it's like 1. And this is my particle notation. Yeah. So this is the marked version. So now it's an important theorem. So I want to give a proof. So you have this 2 category. Then so this extends to a coordinate equivalence. This is marked. This is the scaled now. So you get a coordinate equivalence of this. Right. So yeah, so the main theorem will see that the main theorem just becomes a corollary of this. Okay, so yeah, I'll just state the things that play an important role in the proof, but I want to give the proof, of course. So the following property of locally Cartesian vibrations play the most important role in the proof of the theorem. So yeah, I'll just write the property that I have. So this is the part of this is the vibration section that I have. So this property of our locally Cartesian vibrations. So you have a locally Cartesian vibration of simplicial sets. Now suppose for our B in B, locus B, the infinity category B has an initial object, then suppose you have this right inclusion where so it is the full subcategory of a full simplicial subset of A subcategory or whatever of A spanned by those A's which are initial objects in this category, which P of it. Then, so if you restrict this to the subset that you have, it's a trivial configuration. Moreover, a section of this vibration that we have is initial in this mapping category, this category. If and only if few factors will intervention. So, okay. So this is the proposition that we have. So now finally I can say I won't get into the details of the construction of the section that you have now. You can finally state the 2 categorical, okay. The 2 categorical theorem A, Coulomb's theorem A. So here's the theorem. So you have this functor of Mark II categories. So this is my notation, if you remember, from the first half. Functor of marked two categories. And suppose what is P and what is B? Okay. So fancy A and fancy B. That exists homomorphism G of B takes B to F of A, which is initial. So now localization comes in the picture, but which I had in both these categories. So now yeah. And every marked morphism. So yeah, so this is a marked morphism. This is my notation for a marked morphism. So every marked morphism is initial. And for any marked morphism, so suppose okay, F from Y to Z can be the induced functor set. Oops. Seems to be a comment in the chat. Yeah. Oh, whoops. Yeah, I'm sorry. Yeah. Yeah. You can leave because it's recorded. So people can leave. Well, yeah, I'm about to end anyways. So. Preserves initial objects. Then, so suppose all these things happen, then, so this functor is an equivalence of infinity categories. So again, this is the Duskin nerve. Infinity one categories. So I don't think I have time for talking about the application, but yeah, we can maybe talk about that more later. So yeah, I'll let you stop here then. Thanks for listening.